we're trying to find absolute minimums and absolute maximums. And using the extreme value theorem, we figured out that the absolute minimums and absolute maximums have to be in one of two places. Either they're endpoints or they're critical numbers, which are places where the derivative is 0 or the derivative doesn't exist. So what we can do to find absolute minimums and absolute maximums is first make a list of all of the candidates, so make a list including endpoints and critical numbers. And then for each of these candidates, just plug in each of these x values into the original function. Whichever of those inputs gives us the largest output, that has to be the absolute maximum, right? We knew that one of these possibilities was the maximum, so it's the one that gives you the biggest result. By the same token, whichever of these candidates gives us the smallest result from f of x, that one is the absolute minimum. So sort of a two-step thing, make a list of candidates, which, right, the tricky part is going to be calculating the derivative and finding where it's equal to 0. But once you have a list of candidates, just plug them all into the original function, not the derivative. Plug them into the original function, and just see which one gives you the biggest result and which one gives you the smallest result. So let's look at a couple examples. So first, let's find the absolute minimum and maximum of this function, x squared plus 3x plus 1, on the interval from 1 to 5. Now, this is a parabola, so and it's opening up. So something like this, right? And the minimum for a parabola is going to be, for a parabola that's opening upwards, the minimum is at the vertex. So actually, I think I wanted this to be minus 5 to 1. So as long as this interval contains the x value of the vertex, then the minimum value we find should be the vertex. And we know the vertex formula, right? Minus b over 2a, so minus 3 over 2. So what we should find is that the minimum value is at minus 3/2. So this is a nice sanity check just to make sure that our method for finding minimums and maximums is actually working. For this example, we should get a minimum at minus 3/2. So let's go ahead and do the calculation. Remember, we have to make a list of candidates. That is, x values that might be the absolute minimum or absolute maximum. And always on your list of candidates will be the endpoints, so minus 5 and 1. Now we need to find critical numbers. So to find critical numbers, we need to calculate the derivative of our function. So for this one, it's 2x plus 3. And now we need to find where this is undefined. Right? Any x value where the derivative is undefined counts as a critical number, but there's no such thing for this example. This derivative is defined everywhere. And the other collection of x values is x values where the derivative is 0. So let's take this derivative, 2x plus 3, set it equal to 0, and solve for x. In this example, there's only one x value that comes from this. It's x equals minus 3/2. Okay, so now we'll add that to our list of candidates, so minus 3/2. Now we have a list of 3 candidates. One of these is the absolute minimum, and one of them is the absolute maximum. To check which is which, we just plug them all into the original function. So first, let's calculate f of minus 5. So minus 5 squared is 25, minus 15 plus 1, so that's 10 plus 1, 11. All right. Now f of minus 3/2, this one's going to be a little trickier, so let's see, 9/4 plus 9/2 plus 1. This 9/2 should be negative, right? Because it's negative times, okay. So this is, let's see, minus 9 halves plus 9 quarters is minus 9 quarters, plus 1 is minus 5 quarters. Okay. And finally, we need to check f of 1, which is 1 plus 3 plus 1. That one's easy. Okay. So now we just look for the largest and smallest output. So here's our largest output. So this means that x equals minus 5 is the absolute maximum because it produced the largest output. And here, x equals minus 3 halves, that's our absolute minimum because it produced the smallest output. And it did, so we did find that the absolute minimum was at the vertex, which we knew ahead of time had to be the case. So this is sort of confirmation that this method we've come up with for finding absolute minimums and maximums actually works. Now that we have some confidence that it works, let's try it on an example where we don't know the answer ahead of time. How about this one? So find absolute minimums and maximums for this function on the interval from 0 to 4. So remember, we need a list of candidates. And always the endpoints are on our list of candidates. Now we need to find critical numbers. So let's take a derivative. We get 54 minus 6x squared. Now this is defined everywhere, so there are no critical points coming from the derivative being undefined. So now let's take this derivative and set it equal to 0 and find critical numbers that way. So solving for x, we can move the x's to the left. 6x squared equals 54. Divide by 6. X squared is 9. So x is plus or minus 3. Let me write those separately. Plus 3 and minus 3. All right, so these go on our list of candidates. So plus 3. And, well, minus 3 isn't in this interval. Right? Plus 3 was, but minus 3 isn't in this interval, so we have to throw that possibility out. It just isn't in the interval that we're interested in. So what this goes to show is that the x values that could be your absolute minimum or maximum can depend on the interval that you started with. Right? Because if you have a critical number that isn't in the interval, well, we don't care about it, so throw it out. Of course, it's no surprise that what your minimum and maximum turns out to be could depend on the interval, because after all, the endpoints of the interval are always candidates. So, all right, so now we have these three candidates. So to find which one is the absolute min and absolute max, we just need to plug them all into the original function to see which one is biggest and which is smallest. So f of 0, that's 5. F of 3, that's 5 plus, oh dear, 112 minus 3 cubed is 27 times 2 is 54. Okay, so 117 minus 54, so that's going to be 63. Is that right? Yes. Okay, and then f of 4, so 5 plus 166, I think, minus 2 times 4 cubed is 64, so 171 minus 128, so that's 43. Okay, so now that we have this list, we can just pull off the biggest and smallest outputs. So there's the smallest. So our minimum is at x equals 0, and our absolute maximum is this one. So our absolute maximum is at x equals 3. All right. Now, what we see if we actually graph this function, Let me get GeoGebra, get a new file. Let's actually graph this function. So f of x is 5 plus 54x minus 2x cubed. So this function, let me shrink the x-axis so that we can actually see what's going on here. Okay. And remember, we were going from 0 to 4. So you can see, first of all, there's this critical point down here because of the horizontal tangent line, but remember, that was at minus 3. And that was the critical number that we threw away because we were only interested in x values from 0 to 4. Now, something else to notice about this graph is this graph, if we zoom out a little bit, it clearly doesn't have an absolute minimum or absolute maximum, right? It's cubic, so it goes up infinitely far on one side and down infinitely far on the other side. But again, we were only interested in x values from 0 to 4. And for those x values, we can actually get a graph just for those, from 0 to 4, right? For these x values, right, that's just this red portion of the graph. For these x values, there clearly is an absolute minimum and maximum. There has to be because of the extreme value theorem. But the absolute minimum is this left-hand endpoint, which is what we found. And the absolute maximum, this is a local maximum, but it's only an absolute maximum because of the small interval that we're looking at. So again, we really are taking advantage of the guarantee of the extreme value theorem to find these absolute minimums and maximums. All right, for one other example, let's suppose we have a projectile that we're launching on a ballistic trajectory, that is a trajectory that is only influenced by gravity. It turns out that if you fire your projectile with an initial velocity v and an angle to the horizontal that we'll call theta, the range of that projectile is given by this formula. And g here is acceleration due to gravity. Of course, this formula only works as long as you don't launch things so far up that gravity gets substantially weaker, and also so long as your ranges aren't so far that the curve of the Earth starts to become important. So we are assuming a flat Earth here. But with those assumptions, or with those caveats, this formula will give you the range of a projectile on a ballistic trajectory. This is the sort of thing you might work out in a physics class. We might want to know how far could we launch this projectile. If we have a given maximum velocity that we can launch things at, how far can we reach with this projectile? So, all right, if we want to maximize our range, what we're really looking for is the maximum value for this function, x of theta. And we know how to find maximum values, right? Use this plan where we have a closed and bounded interval and candidate points and so on. Well, to get that all started, to be sure that we have an absolute maximum, we need a closed and bounded interval. So we should think about what limits are there on theta in this problem. Well, theta can't be negative, right? If theta is negative, we're firing our projectile into the ground, and that isn't helpful. That's not going to maximize the range. So the smallest range that we should consider is 0. So what about the largest range? Well, if we're measuring how far the projectile goes to the right, we should make sure that we're actually firing the projectile to the right, which means that the largest angle that we should consider is firing it straight up, and that's pi over 2. Pi over 2, it definitely isn't going to be a maximum, but the idea here is, based on the sort of physical situation, we want to come up with a closed and bounded interval, because that will guarantee that we have an absolute maximum. So for this situation, our interval is going to be from 0 to pi over 2. So now that we have a closed and bounded interval, this function is definitely continuous because it's a product of continuous trig functions. Now the extreme value theorem guarantees that there is an absolute maximum, so now we can go ahead and use our trick to find it. So candidates, The endpoints are always candidates, although we kind of suspect that those aren't going to be the absolute maximum. To find critical numbers, we need to calculate the derivative of the function we're finding the maximum of. Now, something to keep in mind as we calculate this derivative is that v and g, those are constants, right? G is gravity, but gravity we've assumed is constant. And the maximum velocity we can launch at, that's also constant. So we can use, to calculate the derivative, we can start out just using the constant multiple rule. In other words, just copy down this constant multiple, and then take the derivative of everything that's left. So derivative of sine, that's cosine, times cosine with no derivative, plus, and then sine with no derivative, times cosine with the derivative, so that's minus sine theta. So I'm a little bit squashed here. So this is 2v squared over g times, looks like we have cosine squared theta minus sine squared theta. Okay, so we need to ask, where is this undefined? Right, where does this not exist? Well, this is defined for every value of theta, so there aren't any critical numbers coming from the derivative being undefined. So the next thing we need to do is find out where this is 0. So set this equal to 0, and then solve. So I guess we can solve first by multiplying both sides by g over 2v squared. On the right-hand side, that doesn't do anything. The 0 sort of eats it up. And on the left-hand side, it cancels all those constants, and we're left with cosine squared theta minus sine squared theta. All right. Well, cosine squared theta minus sine squared, there are a couple different ways to solve this equation for theta. One nice way is to remember that cosine squared theta minus sine squared theta that's actually part of a double angle identity. This is a cosine of 2 theta. Now we can just take inverse cosine. So 2 theta is inverse cosine of 0. Although we do have to be careful here, because when we write this, remember that there are actually infinitely many solutions to this equation, cosine 2 theta equals 0. Right? They're all plus or minus inverse cosine of 0 plus any multiple of pi, so any multiple of 2 pi, so 2 pi k. But the thing is, remember, we're only looking for candidates from 0 to pi over 2. And there's only a single possibility among all of these angles that will give us a theta value between 0 and pi over 2. So let's just finish solving to see why that is. So divide by 2, so theta is inverse cosine of 0 is pi over 2. So divide by 2, we get plus or minus pi over 4 plus 2 pi k, and k is any integer here. Okay, so if we made a list of all of these, it's pi over 4, and then, oh, I forgot to divide this by 2 here. So pi over 4, 5 pi over 4, 9 pi over 4, and so on. And then going the other way, because k could be negative, would give us negative 3 pi over 4, negative 7 pi over 4, and so on. But again, we're looking for angles in the interval from 0 to pi over 2. And there's only one of these angles that's between 0 and pi over 2. It's pi over 4. So there's one other angle to add to our list of candidates here, pi over 4. Now we need to plug all of these into our range function to see which one gives us the biggest. So remember, our range function was 2v squared over g times cosine theta sine theta. And the theta values that we needed to worry about were 0, pi over 4, and pi over 2. Okay, so let's just plug these in. How about 0? For 0, we get 2v squared over g. Cosine of 0 is 1, and then sine of 0 is 0. So this whole thing is 0. that's not a surprise. Remember, if we launch our projectile with angle 0, that means we're launching it parallel to the ground. Well, it's going to immediately hit the ground if we do that. So no surprise that the range there is 0. For pi over 4, we get 2v squared over g. Now cosine of pi over 4, that's root 2 over 2, times sine of pi over 4, that's also root 2 over 2. So putting this all together, 2v squared over g times, turns out this is a half, so v squared over g. And then our final angle to check is pi over 2, but of course pi over 2 is firing our projectile straight up, and if we fire our projectile straight up, the range that it goes, or the distance it goes downrange is 0. It's just going to fall back on our heads, and in the formula that's because cosine of pi over 2 is 0. Right? Sine of pi over 2 is 1, and so we get 0. All right, so the maximum range is given by the angle pi over 4. So if you are firing a projectile and you want to maximize your range, you should aim upwards at an angle of pi over 4, or 45 degrees.